And we got another DC RC circuit here with resistors and capacitors in a DC circuit. I've chosen to do this problem for you mainly because there's a little bit of math to do in this one, a little bit of algebra, which you might not have seen in quite a while. And I think this was a good one to sort of take it slow and practice it end to end here. So we just looking at immediately at the picture, we see well, a few resistors and a few capacitors in some weird combination. And well, looking at a picture like this, doesn't it just make you want to combine them? I think that is 90% of the time when you see a picture like this, the right move to do to combine them. We did see in the last problem we didn't combine them, and in fact you would have caused yourself some pain trying to combine them. But in this case, that is what we're going to do. Now let's get to reading here. So consider the following circuit where the capacitors are initially empty. And so that is a key word. Capacitors are initially empty is a form of a key word that's sort of telling you that this is a charging circuit. We're starting empty and we're going to charge up until we're full. And it's a three-part question. We love those. Part A, find the current across the battery at a time t equals 0 seconds. Find the current that it would take for the capacitors to be about 63%. Very odd, strange, specific number. Another key sort of should bring back a specific memory. And find the exact time that it would take for the capacitors to be charged to exactly 1 volt. Okay, so for the first part, find the current across the battery. Now that is kind of an indication that we're going to need to think of the circuit as a whole and to figure out what exactly this current is here. That's not something we can very easily find with just a 1 ohms law. We're going to need to know what's happening at the rest of the circuit in order to figure out what's happening at the battery. The second part, find the time that it would take for the capacitors to be about 63% charged. That's a keyword. That is going to remind you of your value tau, which is the amount of seconds when it's 63% charged or 20 or 37% discharged in a discharging circuit. Or sorry, 37% charged in a discharging circuit. And then finally, part C, find the exact time that it would take for the capacitors to be charged to exactly 1 volt. That's a little bit more complicated. It's not this 63% quantity, so we have to do this the hard way using a little bit of algebra. Now in a charging circuit, we have the functional form of the voltage across the capacitor over time. And so if we just had, one simple resistor and one capacitor, across the capacitor, the voltage drop, well, it starts at 0, but it ends to be equal to the voltage across the battery. So this is delta VB, and it follows an exponential decay form. The closer you get to the battery voltage, the harder it is to put any more electrons onto that capacitor. And so we have the functional form. It's like this. It's an upside down exponential decay, and we're going to have to actually use the formula and do some algebra to figure out some time values here. But one more thing to point out is that this value tau is equal to R times C, the resistance value in ohms times the capacitance in farads. You get a time in seconds if you multiply those together, and that time, it's not particularly special, but it's a good gauge as it sort of sets the stage for this curve. This value will be 0.63 or 63% times the total battery voltage. And so at a time of tau, the capacitor will be 63% upway to its full voltage. The reason it's useful, right, if we say take 2 or 3 or so tau values, the capacitor is almost full. It's almost completely full. And so this tau value sort of tells you about how much time needs to pass before we're filling this capacitor. And so it sort of sets the scale. Is that 1 millisecond, 1 microsecond, 1 nanosecond? Depends on the R and the C. Our problem is a little bit more complicated, right? Well, we have multiple resistors and multiple capacitors, but it turns out that we can just, well, make our own circuit. We're going to make our own circuit up where we have one resistor and one capacitor, just like the picture in the previous slide. But this is going to be Req, and this one is going to be the Ceq. And I'll go ahead and put a little box around this one. And the reason is, it turns out we can, because surrounding this capacitor here, surrounding these capacitors, doesn't really affect the rest of the circuit. I can draw a little picture, a little circle around this, and it will not interfere with the resistors. On the other hand, I can draw a little circle around the resistors, and it doesn't really bother, it doesn't interfere with the rest of the circuit. So I could replace this whole thing with an equivalent resistance, and replace the capacitors with an equivalent capacitance, and just pretend that there's only one resistor and one capacitor. Our problem does not change. And so we can do that. Well, actually, we can actually solve the first part without even doing any of that. But if we did, how do we find this equivalent resistance? It depends. Are they in series or in parallel? These happen to be in series, which is good. That means we can add them directly. 64 ohms plus 64 ohms is equal to 128 ohms. Okay, and now Ceq, these happen to be in parallel, and that's also the nice one. We don't have to add this funky upside down way. We can just add them directly. And so 840 plus 970, let's see, 7, 11, 9, 9, 18, 1810 microfarads. Okay, that's 840. And let me double check here. 840 plus 970 is 1810 microfarads. Okay, now we can sort of move on and get to the actual questions. Find the current across the battery at a time t equals 0. Well, at a time of 0, the capacitors are initially empty. And so when they're empty, when you have an electron that comes by on one side of the capacitor, it will go ahead and go through. And I would recommend that you go and watch the previous video to understand that initially the capacitor behaves like a wire, and so it has no voltage drop, and so we can pretend it's not even there. We can pretend initially that it's not even there, and so if I gave you that this is a 2-volt circuit with a 128 volt ohm resistor, then you should be able to find, due to the Ohm's law, that the current across the resistor would be equal to, 2 volts over 128 ohms. 2 over 128, 0.0156, 0.0156 amps. Okay. And just to be clear here, the reason I can say that this is a 2-volt drop is because of the loop law. We go up these 2 volts, we go down some value, and then we go down. Well, the capacitor has a 0 volts since it's behaving like a wire right now, and so we must have gone down 2 volts down the resistor. Now this is the current across the equivalent resistor. Let me say Ieq. But due to the junction law, so if this is Ieq, I equivalent resistor, the junction law says that whenever you see a junction, the incoming current is going to be equal to the sum of the outgoing current. Okay. Well, in this case, there's no junctions. No junctions means that the current will always be the same. It's always going to be 0.0156 amps, including across the battery here, we're going to have 0.0156 amps. Okay, and now that's going to be equal to the I at the battery, and so we're done. This is the same current, and therefore the answer to part A. Okay, good. And so that's one of the 3 questions down. Part B is asking, find the time that it would take for the capacitors to be about 63% charged in total. Now again, that's like a little bit of keywords there. You should just know that that equals, that time is tau, which equals R times C. This isn't the only way to get the answer, by the way, but it's vastly easier. And so all we have to do is multiply the equivalent resistance, 128 ohms, times 1810 microfarads. We don't have SI this time, but that's okay. We just have our answer in microseconds, 1810 times 128. Oh boy, so this is 231,680 microseconds, or let's go ahead and convert that. So micro is 10 to the minus 6, so multiply by 10 to the minus 6, and I get 0.23 2 seconds, let's say, is the tau value, which is the number of seconds that it takes for it to be 63% charged. We don't have to do it this way, but you can see all you had to do was multiply 2 numbers. We can do it the long way, which is how we have to do part C. Let's clear the page here and start with part C. So the way that we do this one, we have to use the equation delta VB is equal to, delta VC is equal to delta VB times 1 minus e to the minus t over tau, or R times C. And our goal is going to be to get to that t value, because we actually have everything else in our equivalent circuit, which I should just draw again for you. This one, we decided that this CEQ was 1810. And that the equivalent resistance was 128 ohms. So we have that R, we have C. E is just Euler's constant. Delta VB is 2 volts, as we see there. Delta VC, well, it's how long would it take the capacitors to be charged to exactly 1 volt. So now we have that as well. We have everything except for T. And so we need to invert this formula and solve for T. I would recommend, and I know the instinct is sometimes to just start putting in numbers and see what works. I would recommend to practice doing this algebraically, which means start from this point, no numbers, and just put in the variables in the right spot until we get T by itself. So my recommendation for how to do that is always to start from the outside in. What's the furthest away from the T? And I would say that the furthest thing is this delta VB. So my first step would be to divide it out from both sides, and I would be left with on the right 1 minus e to the minus t over RC. And again, if I take that algorithm of looking at the thing that's furthest from the t value, in this case it's the 1. And so let me subtract it from the other side. Delta VC over delta VB minus 1 is equal to negative e to the minus t over RC. Okay, now I have this negative sign. That's easy. I can just do that right now. I'll just go ahead and multiply this by negative 1. Multiplied everything by negative 1. And now we're just subtracting out delta VC over delta VB now. Okay, and now how do I get the t out of this exponential? Well, you need to undo an exponential, and so the natural enemy of the exponential is the natural log. Predator to exponentials everywhere, because e to the something, if you take the natural log, that natural log and that e just cancels, is the easiest way to think about it. There's a little bit of hidden math in there, but we don't have to worry about it. What that means is that the natural log of, and I'll just rearrange just to make this a little bit neater, of 1 minus delta VC over delta VB is equal to negative t over RC. And we're almost there. We just to get the RC by itself now, the last thing we need to do is multiply both sides, right? Once again, look at this thing, look at the furthest thing from the t, that would be the RC, and then this minus sign. So we just need to multiply both sides by RC, and then divide by a negative 1. I'm going to do that in one step, and so the sort of answer is going to be negative natural log 1 minus delta VC over delta VB divided by RC is equal to T. And this would have worked. This would have worked in part B. You would have only need to put in 0.63 times times the 2 volts for delta VC, and you would have gotten the same answer, that T is just going to end up being equal to whatever R times C was. We got to this point. The rest is plug and chug. Put in the REQ values, put in the CEQ values, okay? Put in the 2 volts for the voltage at the battery and 1 volt for voltage at the capacitor. So I've gone ahead and done this, and I got that T equals 2.99 seconds. I'm going to say you do this yourself, confirm. I'm not very good at using a calculator, and double check my work and see if we've got the right answer. Let me know if you have questions. This process is not one we've practiced yet, but one that you did in Algebra 2, maybe like, 5 to 6 years ago for some of you, maybe even longer. And so I wouldn't be surprised if this would have given you trouble without seeing it before. Okay, let me know if you have questions. Make sure that on your homework that you actually do this part and plug in all the values. A little bit of evidence that you tried this problem a little bit yourself and didn't just copy my answer. All right, folks, thank you.